Today we'll be talking about how WebAssembly is used in Sybase and the design philosophy behind why we do things the way we do. So what is WebAssembly? WebAssembly is a virtual instruction set architecture designed for use in the web. So WebAssembly has pretty broad support today. Modern browsers have built-in support for WASM, and quite a few languages have WebAssembly backends that they can compile to. We support C++ and Rust because those are two of the languages that have the best WebAssembly support, and they're also ones that we're familiar with. So WebAssembly is designed to compile to fast native code. A WebAssembly module is mostly self-contained. It can only interact with its environment by importing and exporting functions that are explicitly defined. So, well, the WebAssembly spec allows anything to be imported or exported, not just functions, but the only components that we allow to be imported in our system are functions. The advantage of using WebAssembly is that we can build our services using normal programming languages and tool chains and just compile it to run on Sybase. It's also a pretty compact representation, and it compiles to efficient machine code, and it provides strong sandboxing semantics that allow us to control access very tightly. Our general philosophy is that if something can be implemented in WebAssembly, then it should be implemented in WebAssembly. So there are a few reasons for this. The first is that code that's implemented in WASM is much easier to update than code that's implemented in native. So if we make changes to the native code, that requires every single node to upgrade, and coordinating such upgrades across the whole network is quite painful. If it's implemented in WASM, then we can just distribute that WASM through the transactions in the chain, and all nodes will automatically synchronize. Another reason for using WebAssembly is that WebAssembly is sandboxed and it requires a lower level of trust. So we can allow anyone to write extensions for the various pieces, not just a small trusted core of developers. And we can allow those extensions without compromising the security of the whole system. And finally, there's just the fact that native code is really easy to get wrong, especially in a blockchain system. So anything that affects the state of the chain has to be strictly deterministic. Even the slightest difference in behavior, no matter how obscure it is an exploitable bug that an attacker can use to bring the entire chain to a screeching halt. That means that anything that's implemented in native code needs to be specified in excruciating detail, and it has to be implemented perfectly. So there's basically no such thing as a benign bug. In order to make the overall system reliable, we want to minimize the amount of code in this category. Code that's implemented in WASM doesn't need to worry so much about determinism because the WebAssembly interpreter itself enforces determinism. So moving code to WASM takes away one of the biggest sources of vulnerability. So there's a specification for WebAssembly. We're currently somewhat behind the curve. We're using EOSVM, which basically implements the MVP WASM. There have been quite a few features added to the spec since then. We added support for SIMD operations, which is by far the largest post-MVP feature. There are a few other features that I'd like to add, but I haven't gotten around to it yet. And we'll probably add them before we get to a final release because the lack of these features is starting to get in the way of using third-party libraries. The current release of WASI, which is the POSIX subsystem for WebAssembly, is using some features that we don't support, so we're still on an old version of that. By the time we get to release, we'll probably have everything updated to match the most recent specification of WebAssembly. Although we probably will want to be careful because anything that we implement, we're stuck with forever, so we have to be careful about not getting ahead. We're always going to be somewhat behind because of that. Okay, our WebAssembly interface. This here is a list of all the native functions that are available for services. So you can see most of them are for reading and writing to the database. There are a couple of functions for managing the cross-service calling convention, and then you have write console, which is mostly for debugging. So that's it. Right here, you have the complete WASM to native interface. This meets our goal of trying to keep the native layer as simple as possible. So the general execution model for WASM, each service is an independent WASM module. It has its own memory space and they can't interfere with each other. Services only interact with each other by the call host function, which invokes an exported function named called in another service. So this calling convention just uses this serialized buffer, which contains an action structure. And then we implement access control for this by having that action structure include the identity of the caller. The callee can then check that to verify that the caller is authorized. The native layer enforces that the caller accurately identifies itself and doesn't lie. So what do we have in WASM? Account management is fully implemented in WASM. The native layer doesn't need to know about accounts for the most part. There are a few exceptions, but from the standpoint of the native layer, an account is just an opaque 64-bit integer. It doesn't need to know about how you sign for transactions from the account or any kind of authorization. It just treats it as an opaque integer that WASM is responsible for managing authorization. Transaction processing is implemented in WebAssembly as well. There's a service called TransactSys, which is responsible for interpreting the transaction, checking authorization of all the top-level actions, and then dispatching it to other services. Resource billing has not yet been implemented, but when it is, the top-level transaction processing will be responsible for querying the timer and to determine how much time the transaction has taken and deciding who to bill for it. Another major thing that we've moved to WASM is signature verification. So signature verification is fully implemented in WASM. We represent the signatures and keys both as binary blob associated with a service that will be used to verify the signatures. So that means that it's pretty easy for us to add new kinds of signatures. At the moment, we just have ECC with the K1 curve. Adding other curves or other signature schemes is just a matter of adding a new verification service. We've implemented queries against the state and history using WebAssembly. So if you send an HTTP request to the Synode server, it will package up the body and headers of that request and call into a WASM module to evaluate the request. The service that handles it, in addition to having access to the state like a transaction, it also has access to the event log and to the block log. So it can look up whatever data it needs to handle the query. We've been using GraphQL for our queries, but there's no requirement to do so. The request and response are entirely defined by the service. That's one of the really cool features of Psibase, that we can implement queries against the chain in any way you want, as long as it fits within an HTTP request. So there are a few things that we haven't implemented in WASM. The consensus and network protocol is not in WASM. It's actually something that we'd like to have in WASM. The problem is that there are a number of technical challenges that are unresolved, the biggest one being concurrency. So the network protocol needs to support concurrency to be reasonably efficient, but it also needs shared mutable state, and WebAssembly just doesn't handle that very well. We'd like it to be in WASM, but we haven't figured out a good solution to do that yet. Another thing that's unlikely to ever be in WASM is various components for handling node administration, like logging, ports, managing node resources, and the like. So this is for security because these interfaces are inherently dangerous, and we don't really want anything defined on the chain to have access to them. That would imply a fairly high level of trust for the chain, and that should at least definitely be opt-in for a specific chain. And finally, access control for the database is implemented natively, which is actually fairly unfortunate, as it's one of the main reasons why native code needs to have any knowledge of accounts. This is again something that we would like to not have in native and have in WASM instead. It's much more likely than the network protocol for us to get a solution before we get to the final release. And that's all I have for today. Questions?